last lecture we had tried to derive an expression for the self inductance of a coil of a single coil of ns turns placed on the stator of a machine having a salient pole rotor, and that was of the form the self inductance of the stator that the expression that we derived had the form LD plus LQ by 2 plus LD minus LQ by 2 into cos of 2 times theta r. Now, there are a few observations to be made. In this machine we have considered the rotor to have 2 poles. The salient pole structure had only 2 poles. We could go back to that figure and take a look at that. So, this was the salient pole structure that we had considered, and one can clearly see that this has 2 poles, and this is the expression that arises for that machine. In the 2 pole machine, the mechanical angle, we have seen this earlier, the mechanical angle is equal to the electrical angle. If the number of poles increases, then the electrical angle will be correspondingly more than the mechanical angle as compared to the mechanical angle. And while deriving this expression, we are trying to find out the flux linkage in the stator winding, and in order to find out the flux linkage in the stator winding, it is necessary to consider one span of the stator winding, and one span of the stator winding is the distance, the angular distance over which the flux changes by 180 degrees of its electrical variation, right. And therefore, if the number of machine poles is going to increase, then we still need to consider only 180 degrees of electrical variation, which means that the theta r considered has to be basically the electrical angle of the rotor. So, if we all the time ensure that we take the electrical angle of the rotor to substitute in this expression, this equation is valid for machine of any number of rotor poles. This is the first observation that we make. The second one, we notice that the MMF waveform that we took was the fundamental component of the MMF waveform, actual MMF waveform, and in trying to determine the flux generated by the MMF waveform, we are assuming that the flux crosses the air gap and connects with rotor as well. The method by which we determined the mutual inductance is also to determine the flux density waveform around the air gap, and by that flux density what we meant, what we implicitly assume is that all the flux that for which this flux density is responsible, all the flux enters into the stator from the rotor, and similarly here all the flux that is generated due to the MMF crosses the air gap and goes into the rotor as well, which therefore means that the expression we have derived is essentially the magnetizing inductance. In addition to this kind of flux, since the stator is essentially a cylindrical stator, and we have seen in the animation that the stator winding goes through the stator along the axis in a particular slot, and then it comes out of the stator and then travels along the circumference of the machine and then goes in through the slot 180 degrees away, and then further goes along the circumference and may make another turn. So, you have stator winding that lies outside the stator as well, and the flux produced due to this part of the stator winding will not be linking or will not be going through the rotor, and therefore, such flux lines are not really considered in the expression that we have derived. So, such flux lines will essentially be grouped under what is called as leakage flux, and this leakage flux in machines can happen at a variety of locations. This particular location is called as end winding leakage flux or the overhang leakage flux. There may be other forms of leakage flux that exist inside the machine, and since the leakage flux path is very difficult to determine, it is difficult to define an analytically derived expression for the leakage flux, and therefore, it is usual to add a leakage inductance to this expression, and therefore, the self inductance is essentially a leakage inductance plus what we have derived as the magnetizing inductance. And then we said that the machine for which we have derived this is essentially a single coil stator along with the salient pole rotor, and we saw through the animation in the last lecture that coils on the stator are seldom single coils. The phase winding, so to say, if you consider a particular R phase in a 3-phase machine, is almost usually a distributed winding, which means that the phase occupies several slots, more than one, maybe more 2 or maybe more than 2, several more slots perhaps, and the angular separation which is spanned by the coils of a particular phase is then called as a phase spread, and it is for such a distributed winding that we really need to find out the self inductance, which we shall attempt to do now. Now, if you look at such a structure, let us, so here we have a finite element study conducted for a distributed winding on the stator with a cylindrical rotor. Now, note that it is sufficient now to consider a cylindrical rotor, because even for the case of a salient pole machine, what we have achieved through the two reaction theory is that we are considering the salient pole, the effect of the salient pole rotor as having been produced by two cylindrical rotors with different air gaps, one air gap corresponding to LGD, which we designate as LGD, another air gap that we designate as LGQ. And to find out the total flux, we find the flux developed when a particular MMF component is applied on the cylindrical rotor with the gap LGD. then we find the flux generated in the cylindrical rotor with the gap LGQ due to a different flux component, and when we add the two we say that that is the total flux that is generated at a given angle alpha, and therefore in order to do that it is sufficient first to consider the case of a cylindrical rotor, and here we have a setup which is a cylindrical rotor. So here we see that the stator winding is distributed in 3 slots. This is the return path of the stator winding, and these are excited. You find that flux lines go like this, and the air gap flux density can now be determined. But in our attempt to derive the inductance, we started out with the MMF distribution. MMF distribution is nothing but the distribution of H multiplied by L, a scaled version of the H field distribution. And if we now look at the H field distribution for the, if you start with angle equal to 0 from here and then go around the air gap and look at how H is going to vary, that plot looks like this. So here is the H field variation. The x axis is plotted in terms of angle, that is it goes from 0 to an angle of 2 pi. Now you see that the H field variation has a step here and then is more or less constant over this region, and then it displays 3 steps to reach this point, again constant, and then so on. So where is this H field distribution constant? You will find that the H field distribution is constant after you cross this. So from here to here the H field distribution is constant, and when you reach this point, as you traverse from here to here there is 1 step and then 2 steps, and then the third step reaches the other level, after which it is constant again, and then 1 step down, another step down back to this point, and 1 more step down to reach the flat level here. So that is how it goes. Now the question is, why do these steps arise and why is this flat? Now if you want to evaluate H, you would take an Amperian loop, apply your Ampere's rule, which says that integral of H dot dl around a closed loop is equal to the number of turns multiplied by current enclosed by that loop. So if we now, let us say we take this flux line and let us form our Amperian loop around that flux line, so which goes like that. So as you travel around that, you see that n into I is basically the number of turns in this slot plus this slot plus this slot multiplied by the flow of current in each. So that is H into L, and we have already understood that H field within the ion regions is almost 0, negligible compared to what occurs in the air gap. So it is essentially H in the air gap multiplied by the length of the air gap, added these two you add in absolute terms that should equal the number of turns multiplied by current for these 3 slots. Now observe that this will be the same whether you take this flux line or that flux line or that flux line or that or that or that, because for all these cases the number of turns included is the same. On the other hand, if you take a loop like this, then you see that only 1 slot is included within this loop, and therefore you would lose out these two and half of that is consumed here. So that is the reason for the step that you see here. Now assume that the number of slots here is not 3 but more number of slots are present, let us say 4 slots are present, in which case what would happen is this would take 4 steps, 2, 3 and then 4 steps. If more number of steps are taken, then correspondingly the number of steps will be more, and therefore one can understand that in the limit where the number of slots are very large and conductors are uniformly distributed around that distribution angle, then what you would have is that this h variation would be almost a straight line here, and then this area becomes flat in any case, and then again a straight line variation, another straight line variation here. So the MMF or the H field waveform is trapezoidal. So that is the MMF waveform that we have to consider. Indeed what we can say is that in the limit, let us say we have a circular stator, and we distribute the windings in a uniform manner all over this place, and then the return conductors are distributed in a uniform manner here. We can say that there is a uniform distribution of conductors in the stator. Let it therefore be equal to Z conductors per radian. Now if it is Z conductors per radian, what we are essentially saying is that each conductor here which is there has a return conductor 180 degrees away, that the coils are full pitched, and then there are the next turn comes here, next turn comes here and so on, and this distribution is uniform. So there are Z conductors per radian. Now it is easy to appreciate, now here there is a rotor which is cylindrical, and at any angle, let us take an angle here. You have seen how the flux lines look like. The flux lines are going around the distribution like this, and therefore the flux lines, if we plot, would go this way. That will be the nature of flux lines, and if we consider any flux line at an angle of, let us say with respect to the center, let us say that we want to find the MMF at this angle, call that angle as some alpha with respect to alpha equal to 0. Then if we now take an Amperian loop that goes around at that particular angle, then we can see that the MMF or the H dot dl would give us 2 times H into Lg, H at the air gap into Lg, that will essentially be equal to the number of conductors in this region, that is 2 times Z into alpha into the flow of I here, so multiplied by Is, and therefore Hg into Lg is equal to Z alpha Is. So, that is the MMF. This is then the MMF that is acting at a particular angle alpha. So, if you go on increasing alpha, the MMF goes on increasing until you reach the end of the phase winding distribution. After that, irrespective of what loop you take, it is always equal to Z multiplied by the entire phase spread from alpha equal to 0 to the phase spread. Note that alpha is the angle from 0 to this point, which can alternatively be written as Z into beta by 2 into Is, where beta is the phase spread. Phase spread is this angle. Let me denote that by some other color. So, that may not be visible. Let us take green. So, this angle is then the phase spread beta, and the maximum value of the MMF will therefore be Z times beta by 2 into Is. So, this is not equal to this always. This is the maximum value of the MMF, and therefore the plot, as we have seen, looks like this. It reaches a certain maximum. Let us assume that MMF is positive in this area. So, goes this way and then comes down like this. So, this interval over which the MMF changes from one level to another level is the phase spread, and therefore this angle is beta. This angle is beta by 2. So, this is plotted with respect to alpha, and this is alpha equal to 0, alpha equal to pi, 2 pi, and so on. So, if you look back on how we have computed the self inductance for the single coil case, we determined how the MMF distribution is going to look like, and then we found out the fundamental component of the MMF distribution. So, that is exactly what we need to do here. We need to find out the fundamental component of this. This level, as we have said, is Z beta by 2 into Is. What we are drawing is the MMF plot, and this angle is beta by 2. So, how to find out the MMF distribution for this? One can write down the expression equations describing this waveform and then do the Fourier series analysis for this. That is one way of doing it. A simpler way of doing it would then be to first consider the derivative of this waveform. The derivative of this waveform would then look like, from 0 to beta by 2 the slope is constant, so it is a constant value, and then from beta by 2 to this value the slope is 0, so derivative is 0, and then here to here the derivative is again constant and then goes to 0 at this point and then goes high again until this, and so on. This is your waveform. And what is the value of the derivative? Derivative is the slope. So, Z beta by 2 is the amplitude here into Is divided by beta by 2. So, it is Z times Is is the amplitude. So, this waveform looks much simpler to handle. In fact, we can do a little better. What we can do is take the derivative of this also. The derivative of this is an impulse function So the impulse function here, it is a step going down, so an impulse function pointing down. This is also an impulse function pointing down, this is an impulse function pointing up. So here again is an impulse function pointing up. Note that the step levels are all the same, it goes from ZIS to 0 and this value is minus of ZIS. Yeah, so this is minus of ZIS and here it is ZIS again. So the impulse functions will then have a value, the impulse function, this function would be described as Z minus of ZIS into delta, and the impulse function occurs at an angle beta by 2 and therefore it is alpha minus beta by 2. So the strength of the impulse is minus ZIS and it occurs at an angle beta by 2, so it is ZIS delta of alpha minus beta by 2, and 90 degrees of the waveform occurs here, this is pi by 2, so here you have pi by 2, pi occurs somewhere here. So what we could do is we could find out the Fourier series of the impulse function train, which is an easier exercise to do mathematically, and to get to this quasi square waveform, which is the first derivative of the MMF waveform, what we can do is integrate that Fourier series of the impulse function distribution, and then to get to the Fourier series of the actual MMF waveform, integrate once again, because we have done two differentiations now, we go back and do two integrations. So how do we find out the Fourier series of this impulse function waveform? We note again that the impulse function waveform, if you had drawn for the negative alpha axis also, so look at the negative alpha axis, then this function would have continued here and then gone up 0 over some distance and so on. So if you now take the derivative, again there would be an impulse function here of the same amplitude and then an impulse function when it goes down again. So one can see that the impulse function waveform is an odd function of alpha, whatever occurs here is the negative of what is happening here, and therefore if we are going to determine the Fourier series of the impulse function, in that Fourier series we will have only sinusoidal terms, the cosinusoidal terms will not be there, and therefore this can be described as sigma of n equal to 1 to infinity Bn sin n alpha. So we need to find out what Bn is, and to do that what we do is Bn is 2 by 2 pi integral 0 to 2 pi, if the derivative function we call as f double dashed of alpha sin n alpha d alpha, and since the function also has half wave symmetry, these two are negatives, since it has half wave symmetry one can write it as 4 by 2 pi integral 0 to pi f double dash alpha sin n alpha d alpha, and indeed this integration is double the value from 0 to pi by 2, and further we know that we are going to be looking only at the fundamental component, so it is sufficient if we determine B1. So let us write B1 as then 8 by 2 pi integral 0 to pi by 2 f double dashed of alpha sine alpha d alpha, and this f double dash of alpha is an impulse function which occurs at beta by 2, and therefore one can write this as 0 to 2 pi, 0 to pi by 2 delta of alpha minus beta by 2 into sine alpha d alpha multiplied by minus zis, and therefore we get 8 minus 8 zis by 2 pi into sine of beta by 2 is the B1 term. Now how to get this is B1 of the second derivative function. So let us indeed call this as Bn double dash to remember that we are talking about the second derivative function, and from this we need to go to the first derivative function B1 dash. So which means essentially f double dash of alpha, looking at the fundamental component alone, can be written as minus 8 zis by 2 pi sine beta by 2 into sine alpha, and we want to find out then f dash of alpha, that is the fundamental component of the first derivative function. For that all we need to do is to integrate this, and that would give us 8 zis by 2 pi sine beta by 2 cos alpha, and then we need to integrate once again to get f of alpha, which is 8 zis by 2 pi sine beta by 2 into sine alpha. So this is the function that we were looking at that represents the fundamental component of the MMF distribution. Now we can therefore write this as a fundamental, the amplitude of the function f hat multiplied by sine alpha, and this is the actual fundamental distribution. We need to resolve this into two components to be acting along the air gap representative of the direct axis, and another component acting along an air gap representative of the quadrature axis. Therefore what you have, this is similar to what we have done earlier, fd of alpha is then f hat multiplied by cos theta r into cos of alpha minus pi by 2 minus theta r, and fq of alpha, which is a variation with respect to alpha, is f hat into sin theta r multiplied by cos of alpha minus theta r. Similar expressions we have derived in the earlier lectures, you may look back at those expressions. This d expression can be simplified as f hat cos theta r into sin of alpha minus theta r. What do we do with this? Now what we really have is a distributed stator winding, and we want to find out the flux linkage of this distributed stator winding, the net flux linkage of this stator winding. The approach that we will adopt for this purpose is, let me copy this figure. And erase some of the things that are not required. indeed maybe, yeah. So, complete this. Complete. Okay. And then we need to draw the phase spread. So, now we are ready. So, this is the machine that we have. We want to find out the flux linkage of this distributed winding. What we will do is we will consider a small coil, elementary coil out of this distributed winding. Now, let us say that we consider this is your angle alpha equal to 0, alpha equal to 0. Let us take some angle, this is some alpha, and at this angle alpha let us consider a small differential angle d alpha, that differential angle is d alpha. Now, if that differential angle is d alpha, in this small angle there are certain turns that have been included. How many turns will be included? We know that the stator conductors are distributed uniformly at a rate of z conductors per radian, and this is an interval of d alpha radians. Therefore, the number of conductors and indeed the number of turns, because each of these conductors would have a return conductor on the other side, and therefore number of turns is equal to z times d alpha. So, on second thoughts, let us call this angle not as alpha, we will call it as beta, or we will call it as gamma. Beta means something else for us. So, let me call this as gamma. Okay. Beta is the phase spread, this angular separation is beta. So, the number of turns would then be z d gamma. Now, these number of turns form an elementary coil. One can imagine that there is a single coil here with the return conductors here, with the number of turns being z d gamma. So, let us now find out what is the flux linkage of this elementary coil, and let us call that as d psi s is the flux linkage of this elementary coil, that is obtained by the number of turns z d gamma multiplied by the direct axis mmf divided by the reluctance of the direct axis mmf at a particular angle alpha, plus the quadrature axis mmf divided by the reluctance of the quadrature axis at a particular angle alpha, is your net flux linkage. This gives you the total flux and this gives you the number of turns, and therefore it is flux linkage. And Rd of alpha is nothing but the length of the air gap along the direct axis divided by mu naught into r into L into d alpha, where r is the radius of the inner circumference of the stator, and then Rq at alpha is Lgq divided by mu naught RL d alpha, and therefore this expression reduces to d psi s equals z into mu naught RL d gamma multiplied by f hat cos theta r sin alpha minus theta r divided by LGD plus f hat sin theta r multiplied by cos of alpha minus theta r divided by LGQ d alpha. This is our expression. Now, in order to find out the flux linkage of this elementary coil, you need to integrate this. So, the flux linkage of this elementary coil, let me call it as delta psi s, that delta psi s is then integral of d psi s, and in doing this integration we have to consider the coil as is there here. This is one side and that is the other side, and we need to integrate over this range in order to get the flux linkage, and that range is given by alpha varying from, we know that from alpha equal to 0 where this coil elementary coil is located is an angle gamma, and therefore this varies from gamma minus pi to gamma, and that is therefore Z mu naught R L d gamma into integral gamma minus pi to gamma f hat cos theta r sin of alpha minus theta r divided by LGD plus f hat sin theta r cos of alpha minus theta r divided by LGQ d alpha. And now let us do this integration. The first term will have f of cos theta r, f hat cos theta r, integral of sine is minus cos alpha minus theta r, you have LGD going from gamma minus pi to gamma. This is the first term, and this can be written as minus f hat cos theta r by LGD multiplied by cos of gamma minus theta r minus cos of gamma minus pi minus theta r, and cos of gamma minus pi minus theta r is the same as minus cos gamma minus theta r. So, this becomes plus cos gamma minus theta r, and therefore, this first term reduces to f hat cos theta r minus 2 times cos of gamma minus theta r by LGD. The second term is f hat sin theta r multiplied by sin of alpha minus theta r divided by LGQ going from gamma minus pi to gamma, which is f hat sin theta r by LGQ into sin of gamma minus theta r minus sin of gamma minus pi minus theta r and sin of gamma minus pi minus theta r is minus sin gamma minus theta r. So, this gives us 2 times f hat sin theta r sin of gamma minus theta r divided by LGQ, and therefore, the total expression then is delta psi s is equal to this Z times mu naught R L d gamma mu naught R L d gamma into 2 times minus, we can take f hat also outside, minus cos theta r cos gamma minus theta r by LGD plus sin theta r sin of gamma minus theta r divided by LGQ. So, this is the flux linkage of this elementary coil which we have determined. And now, in order to determine the flux linkage of the entire phase spread, we need to sweep this over the entire phase spread. This angle gamma can be anywhere from this level to that level. And how do we do that? Therefore, the flux linkage psi s of the stator winding can be determined as integral of this delta psi s. The angle going from what we need to do is to integrate from here to here, and that this angle, that is the angle at this point, is nothing but pi minus beta by 2. From here to the center point here is pi minus beta by 2 to pi plus beta by 2, and therefore delta psi s going from pi minus beta by 2 to pi plus beta by 2. This time the integration is with respect to gamma. It is gamma that goes from pi minus beta by 2 to pi plus beta by 2, and therefore that would give us psi s is equal to f hat z mu naught r into L multiplied by 2 into cos theta r by LGD multiplied by sin gamma minus theta r. The minus sign remains, going from pi minus beta by 2 to pi plus beta by 2 plus sin theta r by LGQ into cos of gamma minus theta r, and therefore this becomes minus, going from pi minus beta by 2 to pi plus beta by 2, and this term gives us sin of pi plus beta by 2 minus theta r minus sin of pi minus beta by 2 minus theta r. So, this is pi minus theta r plus beta by 2, pi minus theta r minus beta by 2, and this can therefore be written as minus pi plus pi minus theta r. So, 2 times sin sin A cos B, that is sin of pi minus theta r cos beta by 2 is what you would get. To be more specific, what another way in which this could be written, pi plus beta by 2 minus theta r is minus sin of beta by 2 minus theta r, and this expression is pi minus of beta by 2 plus theta r, that is sin of beta by 2 minus theta r, which gives us minus 2 sin beta by 2 minus theta r. And this can be taken forward to further simplify the expressions. Let us look at further simplification in the next class and see how the inductance term is really going to look like for this case of distributed stator winding. We will stop here and continue in the next class.